Okay, so we're talking about the EAY and effective annual yield and other financial matters. And we had just got to this question where we were comparing three different accounts. I didn't actually do the computations, but I wanted to show them to you here. So as I was saying, we have three accounts, each with different uh, compounding periods and different APRs. So let's look at the first one. It's 5.05% compounded quarterly. So 5.05%, that's 0.0505. We divide that by 4, add 1 to it, raise it to the fourth power, subtract 1, and then that is our actual R value. Now, and then you do that. Basically, we just do this 2 more times for these different these other accounts. I guess I should mention, for the one that's compounded annually, that's just what we used to do. So basically, for that one, we just get the, well, we don't do anything. If it's compounded annually, then the APR is the rate. APR and rate are the same in this situation. So there's really nothing to do. And then for the account C, that's 365 because it's daily. And so there you see that computation. The biggest mistake I think that people make on this is they do not put this into the calculator correctly. So let me just show you an example of a correct way to compute this. If you're going to do all of this at once, okay, like this first one, I mean, you can't do all three of them at once. We have to do them one at a time. But if I'm going to input all of this in one computation, here is how you should do it. So use your parentheses. Okay. And that's how you do it. So 0.05146, there you see the answer. All right. Moving along, let's look at another example. $2,500 is deposited into an account with an APR of 6%. Calculate the balance after 5 years if this APR is compounded, a whole bunch of different ways. Okay. So just to set this up, what we're going to do is we've got a fixed initial value, and then we're going to have our formula. We have a fixed APR of 0.06. But then the thing that's going to change is this N. T is not going to change. T is because we're going to do it for 5 years. So T is going to be 5, but N is going to vary for each one of these. So for this one, N equals 1. For semi-annually, N equals 2. For quarterly, N equals 4. Monthly, N equals 12. Weekly, N equals 52. That's the value we use for weeks in a month. And daily, N equals 365. So we just have to run this computation a whole bunch of times. And that's what you see here. Notice also that as we step through these, that we are increasing the number of compounding periods per year. And as we increase that N value, what happens to our outcome of the account? Well, it gets bigger. But it also gets bigger, less bigger, right? So when we jump from weekly to daily, we only have a 50-cent growth. But when we go from annual to semi-annual, we've got about $15 of growth. So that's significant. Now, one way to approach this other than just computing it a bunch of times as given below. So we could type in this as a function, but change the variable. So we could actually let n be the variable and type in our function and put x right here for that n value. And that's what we've done in this slide. And then we just run vars y vars a whole bunch of times, and that's slightly easier. So, you know, if you have to do a problem like this and you want to run through it quickly, then you can do it this way, where we let the variable go there and there. That looks like I'm marking it out. I'm not marking it out. I'm saying that would be my x and that would be my x. But this is a pretty specific thing, so you know you're not going to be doing this very much, but this is one quick way to answer a bunch of them at once. All right, another example. Suppose we have a 1.1% APR. Let's find the account's doubling time if the interest is compounded annually versus quarterly. So to find doubling time, usually that ends up to be a calc intersect question. But so we'll get to that in a moment. But so if it's annual and we have a 1.1% APR, then that's just our rate. So 1.1% is our rate. So our model is going to be a sub 0, that's your initial value, and then that's 1.1, so it's 0.011. So that's 1.011. I'm just adding 1 to that, to the t. And I'll use, for my initial value, let's use a sub o equal to 1. That's the easiest. And so then my model would just be a of t equals a sub 0, 1.011 to the t. And then for y2, we would just put in 2, and we could do calc intersect with this setup to get our doubling time. I'm sorry, that's supposed to be a 1. I said it was 1. Okay. Now for quarterly, we have to use the full compounding model. And again, I'm going to imagine that I start off with $1, but this is going to be 0.011 over 4 to the 4t. So that will be my model. And then as far as computing it, again, y2 would be 2 because I'm just going to double my $1, and I would need to do calc intersect with that. Okay. So to actually compute this, this is for the annual model, what you're looking at here in the first box. And then we get our window as we normally do and do calc intersect, and you get 63.36. For the quarterly compounded model, when you type this in, I would actually, this probably doesn't, you know, I'm kind of paranoid with doing parentheses. So here's the way that I would type this in. Actually, let me just type it in the actual calculator. Here's the way I would type this model in. Let me go back to my original. So there's my model. And to enter it into the calculator, I would do this. So that's a 1, so I don't need to bother typing that, but I could. And then I'll say 1 plus parentheses 0.011 divided by 4, close my parentheses, caret, and then here's a new thing, 4x is that also needs to be in parentheses. Too many. If you don't put parentheses around this 4x, then the calculator will not read it correctly. Okay, so it's very important that you do that. And then we want to intersect that with 2. Let's go to the table and see how long it's going to take me to get there. Oh, so a little while. So I'm at 27 and I'm tired of clicking that button. So you know what I'm going to do? I'm going to make this 100. Now that's not the most accurate way to go about this, but I think it'll work. And then we do zoom fit. And we hope that our window is good enough. If you don't want to do it exactly how I did it, when I jumped to 0 to 100, it was just because I was lazy. But I could have just changed my table set to start later, and then I could have got an exact value. But this, I mean, look, I've got a perfect intersection, so who cares, right? That was a perfectly legitimate method. And our intersection is 63.0999984. Which rounds to 63.1. And that is the end of section 5.1. So from here we'll start talking about exponential decay functions, but we'll do that in the next lecture.